Okay, we ask all the attendees to mute themselves for the duration of the lecture. We also encourage you to all ask questions during the lectures, but please do so in the chat. One of the organizers will communicate your questions to the instructor. You will also have the opportunity to ask questions verbally at the end of each lecture. With that being said, we're excited to have Macarena Arenas speaking on a crash course on isoperimetry. So whenever you're ready, Macarena.
Thank you, Blue. Well, thanks everyone for coming. So today I'm going to switch gears a little bit, and instead of discussing more examples of then functions or properties of groups with certain then functions, I'm going to discuss some generalizations. So I'm going to discuss the conjugacy problem and some variations, some other versions of then functions that one can define. So I'm going to begin just with a quick reminder of what we did on Tuesday. So we saw that there are groups that have then functions that are not bounded by polynomials. So for instance, the Bomsdorf-Solitaire group has an exponential then function. And we saw that there are other groups that have then functions that are towers of exponentials. And we also saw that there are then functions whose isoperimetric there are groups whose then functions are not bounded by any tower of exponentials, but are still recursive. We also discussed the isoperimetric spectrum. So the set of numbers d such that n to the d is the growth type of a then function. We saw that having a subquadratic isoperimetric function implies having a linear then function. And that this implies that the group is in fact hyperbolic. And we saw that IP, so the isoperimetric spectrum, is dense in one union the interval 2, infinity. We discussed some of the ingredients that go into the proof of this theorem. In particular, we discussed snowflake groups, which are groups that have a fractal nature. That some of the diagrams that you see inside them, the diagrams that you use to prove, to estimate their then functions, have a fractal-like nature. Finally, very briefly, we discussed subgroups of hyperbolic groups and what sort of then functions can arise for these. So if a subgroup of a hyperbolic group is, again, hyperbolic, of course, its then function is going to be linear. But we saw that there are examples of finely represented subgroups of hyperbolic groups that are not themselves hyperbolic. So these are going to have then functions that are at least quadratic. And we also saw that these are bounded above, so these are going to be at most polynomial. Okay, so now I would like to tell you a bit about some directions in which one can try to generalize then functions. So topologically, the word problem and isoperimetry is all about understanding the relationship between curves and the disks that are bounded by these curves. And it's very natural to try to replace these objects, so to try to replace curves with other objects and disks with other objects. So what are some natural things that one can try to do? One can replace a curve by a sphere, a higher dimensional sphere. And in that case, you would replace the disk by a ball of dimension, so this should be n, a ball of dimension n-1. And that is sort of like studying higher homotopy groups of a space. Another direction is...
There's a question in the chat. If you're a subgroup of a hyperbolic group, do you have a polynomial Dane function?
Not in general, that just for the examples that we mentioned.
Okay, cool. Thank you.
Yeah, so that's, I'm not saying that that is a theorem in general for all hyperbolic groups. Yeah. Another direction is that we can, instead of study curves, we can study cycles. And then the equivalent of disks would be chains. So this is passing to homology. And a third direction is staying within the fundamental group But instead of looking at curves, looking at collections of curves. And then the natural thing to put here is a surface, which can be connected or disconnected. It can have a single boundary component. It can have a positive genus or have genus 0. So there's a variety of options. And I think that the most natural way to sort of try to start going about these generalizations is to study the conjugacy problem. So the conjugacy problem was introduced by Max Dan when he introduced the word problem, so in 1910. And it asks the following question. So given a finitely generated group, given by a presentation where the generating set is finite, is there an algorithm that decides for any pair of words written as products of elements in the generating set, whether those two words are conjugate in the group, whether they represent conjugate elements in the group? So the notation we're going to use here is W twiddle W prime G. And that means that W is conjugate to W prime and G. So if such an algorithm exists, we're going to say that the conjugacy problem is solvable in G. As in the case of the word problem, I'm implicitly saying that this is well defined for the group, that it doesn't depend on the finite presentation, and that is the case. So this is an invariant of the group. One thing to note is that the word problem is a particular instance of the conjugacy problem. So when one of the elements that we're trying to conjugate is the trivial element, the conjugacy problem reduces to the word problem. So what are some examples of groups that have a solvable conjugacy problem? So hyperbolic groups have a solvable conjugacy problem. One-reator groups with torsion have a solvable conjugacy problem. RAGs and cat-zero groups also have a solvable conjugacy problem. Diagram groups have a solvable conjugacy problem. We haven't discussed diagram groups, but the reason I'm mentioning them is because Thompson's group belongs in this family, and this is a group that we have mentioned before. Finally presented conjugacy separable groups have a solvable word problem, conjugacy problem. This is a theorem of Malsha. Let me remind you what conjugacy separable means. It means that if you have two elements that are not conjugate in the group, then there is a finite quotient where they are not conjugate. Okay, so these are some examples. And now we would like to give a topological interpretation to the problem, as we did in the case of the word problem. So if two words represent conjugate elements in G, the corresponding paths in the presentation complex are homotopic. So there is a disk. Sorry, there is an annulus bounded by these two paths, P and P prime. So the annulus certifies the conjugacy between the two paths. The annulus certifies that there is an homotopy. And furthermore, if we have an expression that certifies this conjugacy, so if we have an element set such that conjugating a W by Z gives W prime, that represents a path that joins the two boundary components of our annulus. Okay, so this is the way we think of this topologically. And as in the case of these diagrams, we have a way to limit ourselves to nice annuli. So an annular diagram is a compact complex that is homotopy equivalent to an annulus and that embeds into the sphere. An annular diagram in X is just a combinatorial map from the annulus into X. And the boundary of the annular diagram is the union of the boundary cycles of the sphere minus the annulus. Now, we have a version of Van Kampen's lemma for annular diagrams, which says that whenever we have two closed paths in a complex, these are going to be homotopic if and only if there is an annular diagram mapping to X, whose boundary is exactly the union of these two paths. So the picture to think about here is that we start with a diagram with an annulus that can be very strange and very badly behaved, but we can always assume that there is one that is nice, that there is one that is just an annular diagram. And therefore, we can think of the two cells of the diagram as being relations, as representing relations in a presentation. Okay, and we can define an analog notion to the one of isoperimetry. For the case of the word problem, we have a way to quantify the conjugacy problem, and the definition is as follows. So if we have a group given by a finite presentation, and we have its corresponding presentation complex, a map is an annular isoperimetric function for the presentation complex or for the presentation. If whenever we have two paths that are homotopic in the presentation complex, there's an annular diagram whose boundary is exactly the union of these two paths, and for which the area is controlled by the function evaluated in the length of these two paths. Okay. And this again quantifies the conjugacy problem in a very precise way, as in the case of the word problem and the classical then function. So if a group has a solvable word problem, then having this should say solvable. Having a solvable conjugacy problem is equivalent to having a recursive annular isoperimetric function. So it's necessary to have this hypothesis here of the group having a solvable word problem, because we saw a few slides ago that the word problem is a particular instance of the conjugacy problem. So if the word problem is not solvable, there's no hope for the conjugacy problem to be solvable either. Okay. So we saw that we can go from conjugation to the word problem by taking one of the conjugate elements to be the identity. There is also a sort of dual to this statement. So if we have a conjugation of this form, this corresponds to an annular diagram. And one thing I can do to this word is the following. So what I'm going to do is I'm going to pass W prime multiplying to the other side. And this gives me a word that is the identity in the group. And this means that there is a diagram, this diagram, whose boundary is this word. So the boundary of this diagram is going to look something like this. Here's W. Here's W prime. And here we have Z. And so the area of this annular diagram is going to be the same as the area of this disk diagram. And the only piece of information that we're missing is the length of the conjugator. So here's where the crux of the matter is. If we could always understand the length of the conjugating element, understanding the isoperimetric problem, the annular isoperimetric problem, would amount to just understanding the classical isoperimetric problem. But understanding the length of conjugators can be very complicated. In general, there's no way to do this in general for finely represented groups. So that's where the complication of the conjugacy problem lies. So one could also, I'm taking here the viewpoint of defining annular isoperimetric functions and translating the complexity of the conjugacy problem to the growth type of an annular isoperimetric function. But one could also take the viewpoint of simply studying the conjugation end function. So this observation allows us to prove a theorem for hyperbolic groups, which is that if a group is hyperbolic if and only if it has a linear annular den function. Which you have probably assumed or imagined. What's the idea? The idea is just that if we have an annular diagram, I'm going to assume that the boundary paths of the diagram lift two geodesics in the universal cover. This is not always the case, but I'm going to assume that for this sketch. Then, because we're in a hyperbolic space, these geodesics fail travel. And that means that at some point they are very close. And the distance between these two geodesics is controlled by the hyperbolicity constant of the space or of the group. So this is a multiple of delta, say n delta, and that gives us a bound on the length of the conjugator. So if we go back to the original diagram, this path comes from a path here that joins the two boundary components, and that is short. So that's how we bound the area of these annular diagrams in terms of the corresponding disk diagrams. Okay, so hyperbolic groups are always a good place to start for sort of trying to prove theorems about this kind of invariance, but they can also be very deceiving because everything behaves very, very nicely in hyperbolic groups. So this theorem might give you the impression that the annular isoperimetric problem is similar to the classical one. And that is not the case. As soon as you leave the world of hyperbolic groups, things get very complicated. So in particular, we know that for the word problem, if a group has a solvable word problem, whenever we have a finitely generated subgroup, then the finitely generated subgroup also has a solvable word problem. Now, the converse is obviously not true, but it is true if you restrict to finite index subgroups. So the question is, how much of the theory generalizes? How much of this is true for the conjugacy problem? And it turns out that none of it. So there are examples of pairs of finitely represented groups, such that one is indexed to in the other one. and one has solvable conjugacy problem and the other does not. So one can make this construction so that the subgroup is the one that has solvable conjugacy problem and the overgroup does not, or vice versa. So one can produce pairs where the overgroup has solvable conjugacy problem and the subgroup does not have solvable conjugacy problem. So this is like a big difference to the word problem. We knew that the word problem was a quasi-symmetry invariant for finite represented groups. The conjugacy problem is not even a commensurability invariant. So that's kind of a very big failure. I don't know how to communicate it in any other way. So this is a result of Neer Collins. And it's kind of a bit, like what do you do if you know that it's not even a commensurability invariant, right? And the thing you can do is try to limit yourself to a class of groups that might behave nicely. So what happens with groups that have a quadratic Dehn function? Maybe in that setting, things are nice. So Rip's question, he asked in 1994, whether having a quadratic isoperimetric function implied that the group had a solvable conjugacy problem. And this seems like a very reasonable thing to ask, because pretty much every single class of groups we know that has a solvable conjugacy problem, that has a quadratic isoperimetric function, also has a solvable conjugacy problem. So in particular, cat-zero groups have a solvable conjugacy problem. The automatic groups, SL and SAS for n larger or equal than 5. Thomson's group has a solvable conjugacy problem. Stalin's group, free bicyclic groups. Nilpotent and polycyclic groups, at least the ones that are finitely generated, have solvable conjugacy problem because they are conjugacy separable. But the point here, the sort of thing that makes us doubt this conjecture, is that there is no unified approach. So the ways people have tried or people have gone about proving these theorems are all very different. They are all very different methods and use very different specific properties of the group. So it's not clear that there is a unified approach to prove such conjecture. And this was an open problem for a very long time, but it's a very recent theorem of Olshanki and Sapir that there actually exist finitely represented groups that have an unsolvable conjugacy problem and a quadratic Dehn function. So Rip's question, the answer is no. The methods in this paper are pretty technical. They have to do with something called S-machines. And this was not a result that just sort of came out of me there. They proved several things that built onto this result, built to sort of produce this result. This is a paper of 2019. And it's 90 pages long about. So you can go and read it if you want. Okay, so maybe this is a good time to sort of change topic again because the conjugacy problem is becoming too complicated. So now let's talk about weak isoperimetric functions. So a function is a weak isoperimetric function for a complex X if whenever one cycle bounds at the chain. So I'm just limiting myself to dimension 2. I'm going to give you the definition in general in a few slides. Whenever a one cycle bounds at the chain, then we have another two chain, so that the boundary of these two chain equals the cycle, and the area of these two chain is controlled by the function evaluated in the length of the cycle. And when the first homology group of the space is trivial, and the group acts geometrically, so properly and co-compacted on the space, then a minimal such F is an invariant of the group. And in fact, is a quasi-isometry invariant. So the notation I'm going to use is this to denote a minimal weak isoperimetric function. These are also sometimes called homological isoperimetric function. The GER stands for Gersten because he is the first person who discussed these functions. This is not standard notation, but the standard notation is very confusing. So this is the notation I'm going to be using for the talk. And the R in the notation references the coefficients because I'm talking about homology and that depends on a ring of coefficients. So this can be Q or R. So this is a minimal weak isoperimetric function. Okay. So what's the picture? What's the idea of what's happening here? The idea is that we have a cycle, which in this case is purple. So this set of curves right here. And it bounds a chain, D. And D is maybe very complicated. Maybe it's a very chunky surface. And the growth type of the function f of the weak isoperimetric function measures how much we can improve this diagram. So we can throw away the original chain D and substitute it for a chain that has ISR amount 5. And we gain control over the size, over the area of this diagram, of this surface, but we use control over its topology. So this can have a very large genus. Or it could have genus 0. We have no idea of what's the topology of this surface anymore. So we gain control the area at the expense of the topology. Because homology does not distinguish between surfaces of different genus. Now, again, for hyperbolic groups, we have a theorem. So if a group is hyperbolic and torsion-free, then its weak isoperimetric function is linear. And this is true for all coefficients. This is a theorem of Gersten. Now, maybe you would expect this to be a characterization of hyperbolicity, like in the case of the classical Den function, but it's not the case. However, we do have a characterization if we are willing to sort of go a little bit beyond the world of hyperbolic groups. So this is a theorem of Eduardo Martinez Pedrosa. So if a group is hyperbolic relative to a finite collection of subgroups, then its Gersten, its weak isoperimetric function is linear, and this is a characterization. It doesn't matter. I'm not going to define what it means for a group to be relatively hyperbolic, but what you should take out of this is that it's a generalization of hyperbolicity. So hyperbolic groups are relatively hyperbolic. And Sahana is going to talk more about relatively hyperbolic groups in her course next week. So if you stick around, you will know what it is. Okay. Now to higher isoperimetric functions. So to the generalization that involves spheres and balls. So first, I'm going to give you a description that does not involve groups in any way. This is just a topological definition. So say X is a CW complex that is K connected. We're going to consider combinatorial maps from the K minus 1 dimensional sphere to X. And we're going to define two notions of volume for these maps. So the filling volume of the map is going to be the minimal K volume of a ball that is bounded by the sphere. So what's the K volume? This is just the number of K cells in the sphere, in the ball. And the boundary volume of the map is going to be the number of open K cells in our cellulation of the sphere. Now, a function is going to be a kth order isoperimetric function for the space X if the following is satisfied. So we want the F volume, so the filling volume of the map, to be bounded by the function F, evaluated in the boundary volume of the map for every non-homotopic map from the sphere into the space. Okay? So this is just a definition. It has nothing to do with groups a priori, it's just about topological spaces. Okay, so how do we make this a definition about groups? If a group is finite represented, then its then function is defined. We have discussed this. And if a group is finite represented, then its presentation complex is finite, is compact. So it has finitely many 2 cells. And this is equivalent to something that is called being type F2. So let me define in general what it means for a group to be of type Fk. So a group is of type Fk if there is a classifying space for the group that has a finite K skeleton. We say that a group is of type F infinity if it is of type Fk for all Ks. And we say that a group is of type F if it has a compact classifying space. Okay. So what are some things to know about these finiteness properties? Some examples. So type F0 is just all groups. All groups are type F0. All groups. Just because all groups have presentation complex, which you build by first adding a single vertex. So the 0 skeleton of the complex is always a finite. A group is type F1 if it's finitely generated. It is type F2 if it's finitely presented, if and only if. This is an if and only if. And for higher finiteness properties, we do not have such a transparent translation into algebraic properties for the group. And what are some examples? So hyperbolic groups are type F infinity. And when they are torsion free, they are also type F. If a group has torsion, it is not type F. Thompson's group F, which we have mentioned a few times in different lectures. It's type F infinity, but not type F, and it's torsion free. So torsion free is not the only obstruction to being type F. Stallings group, which we also mentioned before, is type F2, but not F3. Okay, so these are the properties that we need to be able to define higher isoperimetric functions for groups. So if a group is of type Fk, an isoperimetric function for G is just an isoperimetric function for a KG1, for a classifying space. So you can think, if you want to think of a specific complex, so actually this is for the universe. If you want to think of a specific complex, you can think of the presentation complex that we have been discussing. And a property having a type Fk implies that you can add a finite number of cells to make this complex k-dimensional, and so that its universal cover is k-connected. Okay. So we're going to say that the kth order then function is just a minimal isoperimetric function. For G. Now the growth type of the then function, again, it does not depend on the presentation. It's an invariant of the group, as long as you start with a presentation that has the right finiteness properties. And it is also a QI invariant. One observation is that if G has a k-dimensional classifying space, its then functions, its higher order then functions. How should I put this? Its higher order then functions are going to be linear whenever the order is larger than k. Just because if you don't have any cells, I mean, there's nothing to do. Now we have a version of the isoperimetric spectrum, which we discussed. We have a version for the higher isoperimetric functions. So if a group is hyperbolic, its second order then function is linear. And we also know, for instance, that the kth order then function of z to the k plus 1 is of this type, is of growth type n to the 1 plus 1 over k. And we can define the isoperimetric spectrum in the way that one would expect. So it's a set of numbers such that n to the d is the then function of a group. Okay? And again, we have a density theorem. And I would invite you to try to guess what's the interval in which we have the density. Yeah?
Everything.
Yes, everything. So this was not something that was like known right away. First, people assumed, thought that the interval was 3/2 of infinity. And then they found these examples and they were like, oh, it's probably 1 plus 1 over k to the infinity. But now we know that it's actually just 1 comma infinity. So it's a little bit, I don't know, maybe a little bit disappointing. But it turns out that the higher dimensional then functions are very well behaved and there's no gap in the isoperimetric spectrum. Okay, so that's that. And now I would like to define weak isoperimetric functions in the general case. So a map is a weak n-dimensional isoperimetric function if whenever an n cycle bounds an n+1 chain, then there is an n+1 chain d prime, whose boundary is again the original n cycle, and so that the n+1 volume of d prime is bounded by the function f, evaluated in the n volume of C. So I haven't defined these volumes, but this is just going to mean the number of cells in the respective dimension. So the n+1 volume is the number of n+1 cells, and the n volume is the number of n cells. We're thinking of everything as being combinatorial maps, so this is the natural way to define volumes. As in the case of the one-dimensional homological or weak then function, if the homology in the right dimension is 0 and the group acts geometrically on the space, then a minimal such function is an invariant of the group. And again, it is also a quasi-symmetry invariant. Again, for notation, we're going to write Ger sub k comma r of G to denote the minimal, such a minimal isoperimetric. And again, we can define this for any ring of coefficients. So this can be Z, Q, or R. And in the higher dimensional cases, we also have a theorem for hyperbolic groups. So if a group is hyperbolic and torsion-free, then its higher dimensional weak isoperimetric functions are linear. So this is a theorem of basically Lang and Mineyev. So one of them did some of the coefficients and the other one did some of the other coefficients. I can't remember exactly. But between the two of them, they cover all possible cases. Okay, and you might have suspected this already, but there is a relationship between the higher than functions and the weak than functions, and it's given by Hurevich's theorem. So for k larger or equal than 2, we can replace cycles for spheres and chains for balls to get the following bounds. So when k is larger or equal than 2, the kth order then function is asymptotically smaller than the kth order weak isoperimetric function. When k is larger or equal than 3, in fact, these are equivalent. In the remaining cases, what do we have? So it's a theorem of Young that there are groups, there are examples for which the second order then function grows strictly slower than the second order weak isoperimetric function. And the remaining case is what happens when k equals 1. So that's a theorem of Abrams, Brady, Danny, and Young. They produce cat-zero groups that have subgroups such that their one-dimensional weak isoperimetric functions are bounded above by a polynomial of degree 5, and whose one-dimensional then functions, so their classical then functions, grow faster than a polynomial of degree d for a chosen d, or even faster than e to the n when d is chosen to be infinite. The main ingredient to prove this theorem is Vezvina-Brady-Morse theorem. So they use Vezvina-Brady-Morse theory to produce groups with interesting finiteness properties, and they produce a sort of mix of a group with interesting finiteness properties with a group that they know has a large then function. Something to note here is that it also follows from Vezvina-Brady-Morse theory that there are groups that are of type FP2, but that are not finitely represented. So I didn't define what FP2 means. These are homological versions of the finiteness properties we discussed. So you can think of this as meaning homologically finitely represented. And Vezvina and Brady produce examples of groups that are of type FP2, but not finitely represented. And why is this relevant? Because it means that there are groups for which the weak then function, the weak isoperimetric function, is defined, but the classical then function is not. So the weak then functions are defined for larger classes of groups. Okay, so now I would like to switch gears again for one last time to go back to the fundamental group. So we're going to, instead of look at just a single curve, we're going to be looking at collections of curves, and we're going to be looking at surfaces bounded by this collection of curves. So a definition, if we have a collection of closed paths mapping to a complex X, then we're going to define the G area of the collection to be the infimum over all the areas of surfaces of genus G that map to the complex and that have that collection of paths as their boundary. Okay, so we're going to be measuring the area of all possible surfaces. In reality, we want them to be surface diagrams, but I'm not going to get into that sort of technical detail right now. So you can think of these as just being surfaces that map into X and that have genus G and that have the same boundary, that their boundary is exactly the collection of paths. So that's the G area of the union of the collection of paths. So what's the picture to keep in mind? So if G equals 0, we're looking at surfaces of this kind, and we want to look at the minimal area of a surface of this kind bounded by these paths. If G is a higher genus surface, for example, here we have genus 4, we want to minimize the area among all surfaces with that specific genus. And that's the area of the collection of paths, the G area. Okay, so now we can define generalized isoperimetric functions. So the Gn isoperimetric function for a complex X is going to be the following map. So it's the supremum over all G areas of collections of paths such that the sum over the length of these paths is exactly m. So the function at the value m is the supremum over all G areas of collections of paths whose length is exactly m. And we're taking the supremum over collections of paths such that their G area is finite. So we want there to actually exist diagrams that satisfy this condition. That's what I'm saying. And now this is my 1 minute of self-promotion. So for hyperbolic groups, we also have a theorem that identifies the growth type of the generalized isoperimetric functions. So this is a theorem of myself and Weiss. So if a group is hyperbolic and torsion-free, then it satisfies a linear Gn isoperimetric function for all possible values of G and N. And yeah. So I think I'm going to finish by telling you about some questions. So first, I would like to remark that the conjugacy problem for one-reactor groups is open. So we discussed that the word problem is solvable for one-reactor groups. And we mentioned that for one-reactor groups with torsion, the conjugacy problem is solvable. But for one-reactor groups in general, it's not known if the conjugacy problem is solvable or not. So that's sort of one big thing that is open, and it's kind of quite surprising because you would think that one-reactor groups are sort of easy, but that's not the case. So also we mentioned that the way we get examples of subgroups of hyperbolic groups with large then functions is by a failure of finiteness properties. So one interesting thing is to find type F subgroups of hyperbolic groups that have large then functions. It might be that this has already been settled because there is a very recent paper on the archive from like 2 weeks ago by Italiano Martelli and Migliorini, where they produced an example of a hyperbolic group with a type F subgroup that is not hyperbolic. So that would give an examples of subgroups of hyperbolic groups that have large then function and have nice finiteness properties. And again, so sort of the question that we have been asking the whole mini course is what makes a group have a quadratic isoperimetric function, a quadratic then function. This is still quite mysterious, and it's not very clear how to unify sort of this property for groups. And lastly, I would like to acknowledge some things that I did not talk about, because either I don't know enough about them, or because there wasn't time, or just because of my personal preference. So this is just a very long list of things that are related to then functions and to the word problem and conjugacy problem that you might be interested in looking into, and you know, that are related to what we discussed in this mini course. So I think I'm going to close with this. Thank you very much.
Thank you. Do we have any questions for Macarena?
Maybe you should stop recording now, Abdul.